Well, we will continue studying simple systems. So we are studying simple systems not to study systems. But to study method and phenomena. So for each phenomena, I am trying to find the simplest system where we can see it for the first time. Now, today, we will study the following phenomena. First, so-called conservation laws. In quadratic systems. Then, second, we will study oscillator using functional integrals. And we will see the issue of ultraviolet infinity. And then we will study infrared anomaly in quantum mechanics. So this is my plan for today. So let me start with functional integral over dx e to the minus m dx over dt squared over 2. Sorry, not minus. I over h. And let me integrate with the following boundary conditions. X at 0, integral from 0 to t as always. X at 0, let me take it to be 0. And let x of t be also be 0. But now I'm not going to study just this integral. My object of study would be so-called correlators. And here, local observables in Feynman sense. I will call it this, Fs. 1 at point T1, O, N at point Tn. So what people in the approach of functional integral mean by local observer? OI is a function of x or I at t. Dx over dt, d2x over dt squared, etc. Finite number of derivatives. In particular, e to the okay. So I just want to say that just finite number of derivatives. Now, the question would be how to compute it. Let us start with something very simple. And the simplest case is to consider x at t1, etc., x at tn. And let me call this object I t1 tn. So my goal would be the following. I would like to compute it. And I will compute it using two tricks. Not two tricks, two techniques. Technique number one. Reduction to Gaussian integral. So what do I mean by this? I mean the following. Let us study, instead of this object, I that depends on the rho, where rho is a function on this interval. So rho is a map, 0t to real numbers. Then I'd like to do the following. So I'll save my space and I write it as I depending on the rho. And here I put rho of t, x of t, and I integrate over dt. So this I is a functional. So would I know this? I of T1 Tn would be just variation with respect to rho of T1, variation with respect to rho of Tn applied to I of rho. Okay. Now I'm ready to compute it. And what is important is that it is a Gaussian integral. And since it's a Gaussian integral, it may be computed by the shift of an argument. Equals, so here is some number that I don't need. It's an useful formula. So let me check with the sign. Sign is wrong. Here the sign should be plus.
Oh, please turn the camera to the right a little bit.
Okay, thank you. So what should be the sign here, plus or minus?
I think plus, since we multiply, we should add a negative and a positive to the exponent. And to complete the square, you need a negative part.
Yes, that's why sign here is plus. Now, what is our A? So what is our Y? Our Y is, of course, the function x of t. What is our A? Our A is an operator, I over H minus I over M d2 over dt squared, right? What is our B? Our B is, of course, rho. So what does this thing mean? Let G of tt prime be a green function for this operator. Then the integral is e to the rho of t, gt t prime, rho of t prime. And here we have a double integral. dt dt prime. So in order to compute it, we need to compute the Green's function. Definition of the Green's function is minus IH m d2 over d square on g t prime should be delta function of t minus t prime. And of course, g at 0, 0 equals to g at 0t equals to g of t0 equals to g of tt should be equal to 0. Okay, so we have this factor. We will take it into account later on. But how to solve this equation? This equation means that to the left, that on the left of t prime, so what I write here, t 0, t capital, and here I have t prime. I should have a motion like this. Gt t prime should be equal to alpha t. For t less than t prime. T prime should be equal to what? To beta. T minus t. For t bigger than t prime. It's not a function, it's multiplication here. So our goal is to find alpha and beta. How to find alpha and beta? So one equation comes from the fact that these two lines should be equal at t equals t prime. So it means that alpha t prime equals beta t prime minus t capital. Okay. but it's only one equation. What is the second equation? dg over dt is alpha for t less than t prime. dg over dt equals beta for t bigger than t prime. So we know that to get a delta function, so here it's a g. And here we have dg over dt. And here we have t. Then this jump must be equal to 1. And it means that beta minus alpha should be equal to 1. It's equation number 2. So that is how I can get this g. Okay? So from this I see the following. I see that beta equals what? T prime over T capital. Probably with the minus sign. And what is alpha? Alpha is 1 plus beta. So alpha equals to T minus T prime divided by T capital. Okay? So I found it. So the result is T minus T prime multiplied by T over T for T smaller than T prime. And here I have T capital minus T prime divided by T. For T bigger than T prime. You may see that there is a symmetry. If I interchange T and T prime, this formula would change, would go into each other. So it is just explicit green function. Okay? Having this green function, I may compute correlators. Important thing that I need to divide by this. So in particular, correlator T1, T2 equals just this function, T minus T prime times T over T capital. And then I need to divide by M over H. Here I have I, M, H. So this is also written as correlator of X of T1, X of T2. It's another notation for it. Now, how to get correlator of dx over dt1? Okay, t and t prime. Dx over t and t prime, sorry. X of t prime. I just differentiate. And I see this jump. It is another theta function. Do not mix it. It is a step theta function. And then I think there is T capital. I am not quite sure about this T capital. One second. No, it was just alpha. One second. Okay, so there is some formula. I can even try to write it down. t minus t prime divided by t. Plus another formula. Also divided by t. So main message is that and here is also prefactor. And prefactor is, okay, let me write this one. IHM. So the main thing is that jump is IH over M. So doing this computation, I have seen that dx of t over dt x of t prime is discontinuous with such a jump. Has a jump at t equals t prime. And this is the value. With value IH over M. Let me take this M back here. So the jump is I times H. At the same time, we know that in classical mechanics, M dH over dt is known as momentum. So we see that momentum and coordinate have a jump that equals to IH. So let us remember this. Let me give you another approach. Another approach is the following. Let me make a change of variable. I can write identity. This identity is called word identity. So let me see how much time do I have. I have some time. 1 second. People are asking. I would like to put here epsilon. And consider terms linear in epsilon. Zero equals 2. We assume that measure is invariant. So we ignore it here. Now we have some term from the exponent. There would be a term like this. IH 2 goes away. M D D what? I can easily integrate by parts here. Sorry, I wrote it wrong. So here I have dx, sorry, dx over dt squared. Squared. So that's why here I have dx over dt and here I have d phi over dt. And here I have x at t1, x at tn. But it's not all. Plus, I have integral dx exponential I over h to the same term. And here I have sum over a x t1 phi ta x tn. A goes from 1 to n. So this is the word identity. So what do this word identity are telling me? They are telling me that thing. I will not rewrite it again. X from T1, X from Tn. And if I take the derivative with respect to T1 squared here, I'm getting it integrating by parts here. I am over H. Sorry. I'm sorry. Is a sum from A, starting from 1 and going to n, I, T1, TA excluded, Tn. I'm sorry. I am sorry. You see, I'm just trying to rewrite it down. It is a sum of delta function. This is another way to get the same result. Just by solving this system of equations. Okay. Now we need to have a 10-minute break.